Hello dear students, in this video I'll continue with revision for term 2. I'll continue with differential equations. In my previous video I have discussed about growth and decay models where we have solved problems from the exercise question from R.D. Sharma book on population growth, then compound interest and radium decomposition or carbon dating. In this video we'll continue with the remaining models, which is Newton's law of cooling and drug assimilation. First, let us have a recap of what is Newton's law of cooling. The rate of change of temperature T of a body is proportional to the difference between the temperature of the body T and the temperature of the surrounding medium A. That is, we have the rate of change of temperature, it is proportional to, this is proportional to T minus A, or we have this expression dt upon dt is equal to minus k into T minus A, where k greater than 0 is a constant. Here we have a negative sign because the temperature is decreasing. If T is greater than A, then we have this dt by dt less than 0, which means the temperature of a body is a decreasing function of time and the body is cooling. On the other hand, if the temperature of the body is less than the temperature of the surrounding, then we will have dt by dt as more than 0. It means the temperature of the body is an increasing function of time and the body is heating. And now we will see a problem based on this. The temperature of a body falls from 84 degrees Celsius to 64 degrees Celsius in 30 minutes when placed in a surrounding of constant temperature 24 degrees Celsius. Express the differential equation for rate of change of temperature. Also find the general solution. Find the time taken for temperature of the body to become 56 degrees Celsius. Similar questions can be expected for 4 marks. The first subdivision carries 2 marks and the second subdivision carries 2 marks. Now let us go about with this question. Now let us take, let T be the temperature at any time T and let A be the surrounding temperature. Then by Newton's law of cooling, we have dt upon dt is proportional to T minus A, or we have dt by dt equal to minus k into T minus A. Now this we can write it as dt upon T minus A equal to minus k dt. When we integrate this on both sides, we get log T minus A equal to minus kt plus c. Now this is log T minus A to the base e. So by the definition of logarithms, we have T minus A as e raised to minus kt plus c, or it is e raised to minus kt into e raised to c. This e raised to c, let us write it as lambda. So this implies T minus A is equal to lambda into e raised to minus kt. Here it is given the surrounding temperature is 24 degrees Celsius. Given A is equal to 24 degrees Celsius. If we take this as 1, so 1 implies T minus 24 equal to lambda into e raised to minus kt. So let us take this as 2. And now, so this is the first subdivision. So this is the general solution of this differential equation. And now moving on to the second subdivision. Find the time taken for the temperature of the body to become 56 degrees Celsius. Now before this, let us find other values. So here it is given the temperature of a body falls from 84 degrees Celsius to 64 degrees Celsius in 30 minutes. It means when T equal to 0, the temperature is 84 degree Celsius. So from 2 we have 84 minus 24 equal to lambda into e raised to 0. Or from this we get lambda is equal to 60. So we have T minus 24 is equal to 60 into e raised to minus kt. Let us take this as 3. And now we have when the temperature of the body falls from 84 degrees Celsius to 64 degrees Celsius, the time taken is 30 minutes. So when T equal to 30 minutes, the temperature falls to 64 degrees Celsius. So from this third equation we have 64 minus 24. It is equal to 60 into e raised to minus 30 k. Here we are substituting for T64 and the time small t as equal to 30. So we have this expression. So from this we get 40 is equal to 60 into e raised to minus 30k, or we have e raised to 30k as 60 upon 40. This is nothing but it is 1.5. So we got e raised to 30k as 1.5. If we take log on both sides, we have 30k log e. Log e is 1 equal to log 1.5. So from this we have k is equal to 1 by 30 into log 1.5. Let us take this as equation 4. Now we need to find the time taken for the temperature of the body to become 56 degrees Celsius. To find T for T is equal to 56 degrees Celsius. Here in equation 3, if we substitute for T equal to 56 and K equal to 1 by 30 log 1.5, we will be able to find T. Three implies 56 minus 24 equal to 60 into e raised to minus 1 by 30 log 1.5 T. So 56 minus 24, it is 32. 32 is equal to 60 into e raised to minus 1 by 30 log 1.5 T, or we have e raised to 1 by 30 log 1.5 T as 60 upon 32. Now 60 upon 32, it is 1.875. If we take log on both sides, we get 1 by 30 log 1.5 T equal to log 1.875. From this we can find T very easily. So this implies T is equal to 30 into log 1.875 upon log 1.5. All these are to the base e. Here the values of log 1.875 is given and log 1.5 is also given. We can substitute that and we can find the value of T. So this is equal to 30 into 0.6286 upon 0.405. Now this comes to be approximately equal to 46.5, or it is 47 minutes. So the time taken for the temperature of the body to become 56 degrees Celsius, it is 47 minutes. So the first subdivision carries 2 marks and the second subdivision up to finding The expression for K carries 1 mark and the final answer carries 1 mark. Now moving on to the next model, which is drug assimilation model, where we will be able to find the amount of drug that is in the body at any time t. So first we have, if a single pill is taken and if no more drugs are taken later, then the rate of change of drug in the gastrointestinal tract, it is given by rate of drug intake minus the rate at which the drug leaves the gastrointestinal tract. So if we take x of t as the amount of drug at any time t in the gastrointestinal tract, and x of 0 is the amount of drug which is taken initially, or it is given by x naught, then we have the rate of change of drug in the gastrointestinal tract, it is equal to dx by dt. This is proportional to the amount of drug which is there. So dx by dt is proportional to x. So we have to use the same relation if we are given problems on drug assimilation. Now moving on to the next question. This question I have taken from Oswald's self-assessment paper. It is a case study question which can be expected for 4 marks. Doctors have shown certain drugs leave a person's bloodstream at a rate that is proportional to the amount present. In an experiment, a patient is injected with 450 milligram of a substance. 7 hours later, it is found that 50 milligram of the substance remains. Assuming the proportional model is correct for the particular substance, express the differential equation that models this scenario. Also find the general solution. Find the time constant K. So here it is said certain drugs leave a person's bloodstream at a rate which is proportional to the amount present. And in an experiment, a patient was injected with 450 milligram of a substance, and 7 hours later it was found that 50 milligram remained. We have to express the differential equation which will model this scenario, and we have to find the general solution. So let us do that first. Now let us take, let x be the amount of drug at any time t, and x naught is the drug which is taken initially. So we have dx by dt, it is proportional to x. That is what is given here. It is proportional to the amount present. Or we have dx by dt is equal to minus kx. We have a negative k because here k is positive. We have a negative k because over a period of time, the amount of drug reduces in the body. So now we can use variable separable. We have dx by x is equal to minus k dt. This when we integrate on both sides, we get log x is equal to minus kt plus c. From this we get x is equal to e raised to minus kt into e raised to c. This e raised to c, let us write it as lambda. So it is lambda into e raised to minus kt. At t equal to 0, we have taken x naught is the drug which is taken initially, that is at time t equal to 0. X equal to x naught. So this implies x naught is equal to lambda into e raised to 0. So we get lambda is equal to x naught. Therefore the model is x is equal to x naught into e raised to minus kt. So this is the required model. Here finding the integral up to this step carries 1 mark, and the final solution, this carries 1 mark. Now moving on to the next subdivision. Find the time constant K. So we have to find K. Now let us see what is given here. It is given a patient is injected with 450 milligram of a substance. So initially 450 milligram of the drug is injected. So given x naught is equal to 450 milligram. So from 1 we have x is equal to 450 into e raised to minus kt. Let us take this as 2. And then it is given 7 hours later, it is found that 50 mg of the substance remains. So when t is equal to 7 hours, x is equal to 50 mg. So from the second equation we have 50 is equal to 450 into e raised to minus 7k. So here we are putting x as 50 and t as 7. Or we have, this is 1 by 9. So 1 by 9 equal to e raised to 7k or e raised to 7k equal to 9. So if we take log on both sides, we get 7k as log 9. Log 9 it is given in the question, it is equal to 2.197225. So this is equal to 2.197225. So from this we have k is equal to 2.197225 upon 7. Now this when we simplify, we get it as approximately 0.31. Here the time constant k, it is per unit time. Here the unit of time is hour. So we have k is equal to 0.31 per hour. So this is k. I hope this video was useful for you. Thank you for watching.